Swayam Prabha. Digital India. Educated India.
Welcome back. Let's resume our study of this new algorithm or new approach to planning, which is operates in the plan space, and the only objects we reason with in it are plans, and of course actions have preconditions and post conditions which come from the predicates, and we saw that every plan space planning algorithm begins with an action A0 which has no preconditions, and it produces the start state predicates as its effects. And every plan or partial plan has one more action, which is A infinity or the last action, and this consumes the goal state and has no effects. Now, we had said that there is a notion of a flaw in a plan, and there were two kinds of flaws that we spoke about. One is open goals. So, for example, when we start with A0 and A infinity, the A infinity action has two open conditions on AB and on table B, and what the planner needs to do is to resolve flaws or remove flaws, and the way to remove the flaw which is an open condition is twofold. One is that either you find an existing action which provides the support or the causal link needed for that. We saw that as an example for clear B, we found that being produced by A0 action, and we just established a causal link between the two. If an existing action cannot provide this causal link, then we add a new action, and we did this in the case of both on AB and on table B. For on AB, we introduced an action stack AB, and for on table B, we introduced the action put down B. Obviously, you can see that once you introduce these new actions, they will have their own preconditions. So, you would have new open goals. So, the planning algorithm would still have more work to do. The other kind of flaw that a partial plan may have is that some action may be threatening to undo the precondition of some other action. So, we saw various examples there, and in this particular example that we were looking at, we saw three flaws, and because of those three flaws, we ended up introducing, for example, these kind of ordering links which said that you must do put down B before you pick up A, because you wanted arm empty to be empty essentially, and otherwise that condition was not met. Then eventually, when we have a partial plan which has no flaws, then we call that a solution plan, and in this particular case that we saw of a one arm robot working for us, there were only linear plans possible, and it is not a surprise that for this problem that we had to solve, there was a linear plan of 4 actions: unstack BC, put down B, pick up A and stack it onto B. Now, we had said at the end of the last session that what if there were multiple arms or multiple agents for that matter, in which case many actions could happen in parallel. So, we had posed this problem in the last time, that how can we reason or how can we model multi-arm robots, and we will see that we are talking about quite versatile robots to do what we have been so far calling as plan space planning, but it is also called partial order planning, because the plan that it produces is a partial order, and as we will see that if you have 2 arms, you can indeed get a partial order which is not necessarily a linear order. It is also called non-linear planning because you do not grow the plan from one end or the other, you can add actions at any layer, because depends on which flaw that you are trying to resolve, you would add an action to or some other condition, maybe a causal link or maybe an ordering link to the plan. It is also called least commitment planning, because what it does is that it identifies actions that have to go into the plan but it waits till it knows something more before it decides the order between actions essentially. So, in that sense it does not commit itself to order as it finds the actions, and we have seen that in the algorithm that we have seen so far, especially forward state space search and backward state space search, the moment they pick an action they know where to place it in the plan, but plan space planning is more flexible on this matter and it waits for a need to induce some order onto the graph. So, this is a problem that we had looked at as a detailed example, and we had said that there is a single armed robot which is solving this, and we had asked the question as to what would happen if there were 2 arms for this robot. So, for the single arm robot it was only possible to construct a sequential plan. If you remember, the plan was pick up, unstack B from C, put it down, pick up A and stack it onto B. But what if there were 2 robots, as is the case that we are investigating now. So, now we have a situation where we have 2 robots, or we have one robot with two arms. As far as we are concerned, the arm is the effective part of the robot that we are interested in. Then what should be the plan? How do you model the domain first of all, and how long would the plan take to execute? So, there are 2 kind of metrics that we use in evaluating plans. One is the number of actions in the plan, and the other is the time taken to execute the plan, which in the planning community we call as make span. Now, the make span is equal to the number of actions in the plan if the plan is a linear plan, because actions have to be done one after the other. But if actions can be done in parallel, then the make span can often be less than the number of actions in the plan, and this is what we want to investigate now, essentially, that if we had a 2 armed robot here solving this problem, how fast could it solve it. So, this is an exercise which I had left you with. I hope you have done some work on this, that how do you modify the strips operators to cater to a domain with 2 armed robots, and also what if we had a 3 armed robot or a 4 armed robot, multiple armed robots or something, would your solution extend to that situation as well. I had also introduced a new problem which was part of a exam that I had given to students here in IIT Madras, and in this problem we have on the left hand side the start state where D is on A and C is on B, and we have 2 arms, and we have to produce a stack which says D should be on C and C should be on A. We do not particularly care whether A is on the table or whether A is on B, for example, that is only block left, and we do not even care whether B is on D or for that matter. The only thing we care about is that C is on A and D is on C essentially. And how would the 2 armed robot, how would you model the operators for a 2 armed robot, and we would like to see what the solution plan looks like essentially. We had also very quickly said that the simplest way to do this is to introduce 2 actions for each of the arms. So, instead of saying, for example, that we have stack A B, and instead of saying that you are holding X, or we specify as to which arm is holding X. So, we could modify the predicate to say that holding 1 and holding 2 are 2 predicates. Holding 1 means that arm 1 is holding X, holding 2 means that arm 2 is holding X, and likewise for the arm empty conditions. And so, that would be a kind of a very trivial solution, where you just say 2 operators for 2 arms, and what you have is an operator called stack 1 and another operator called stack 2, but they are identical in other ways, except that the predicates that they use are slightly different. Stack 1 has a precondition, stack 2 has a precondition that holding 2x, and stack 1 has a precondition that holding 1x essentially. Now, obviously, this will work for a 2 arm robot, but it would be difficult to replicate with multi arm robots essentially, especially if you allow more flexible actions that we will see in a moment. Okay, so again the same question, what if the robot had multiple arms? Now, one question that we have kind of not addressed in detail is that when you pick up an object x, for example, or when you unstack x from something else, then should you delete clear x or should you let it be essentially. So, the operators that we have introduced so far did not do anything to clear x, and for example, when you unstack a from b, a was clear, but it does not show anywhere in the effects of the action, which means that we are not deleting it essentially. So, it is a question of semantics, that if you are holding that object A, can you say that it is clear or can you say that it is not clear essentially. So, obviously, if you take a more physical perspective, then it would depend whether how the robot is holding the object. If it is holding from the top, then clearly that object would not be clear, but if it is somehow holding it from the side, then you can imagine that it is clear essentially, and as you will see in practice or in principle, we can imagine stacking another block onto that essentially. But the algorithms that we had written, we had not deleted clear B, deleted clear A from this thing, and therefore, we had to do nothing for that for the case of stacking that object. But now, supposing we do delete this predicate. So, for example, when we unstack A from B, we say that A is no longer clear as shown here in red. So, in blue it is the precondition, and in red it is the post condition that we are saying is no longer clear. So, if it is no longer clear in this one armed robot case, it does not really matter whether you delete this clear or not, because the only thing you can do with an object that you are holding is you can either put it down or you can stack it onto another object. So, if you were to stack A onto B for some reason again, then we would have to add clear A again. So, if you unstack it, you have to delete clear A, if you stack it, you have to add clear A, and in a one arm robot it does not really matter, because it simply is going to not change anything, and you might as well say that okay, this let us not delete clear A, because it is less work than deleting it and adding it again essentially. Now, look at this plan. In this plan, we have assumed that we are going to add this delete action. So, as you can see, when you unstack D from A, D had to be clear, and then we have added as an effect not clear D, or in other words we have deleted clear D from its effects. The same thing for clear C on the right hand side, and we have deleted clear C essentially. Now, because of the fact that we are deleting clear C, action stack D onto C needs clear C, as you can see, and we have to wait for stack C on A to finish, because that would add clear C and that would provide this causal link here for this action. So, this is a partial plan, that is the plan without flaws. There are two actions, one is to do with unstacking D from A and afterwards stacking D onto C, and the other right hand side is to do with unstacking C from B and then stacking it onto A essentially. And this is a partial plan which has no flaws. The maroon colored links are the ordering links, the dotted arrows are the causal links, as we have seen before. So, in this plan there are no flaws, and so it is a solution plan. I encourage you to take this up and work on it a little bit and see that it is indeed the plan that you will generate. Now, we had also talked about multi-armed robots. So, let us look at this question again. If we want to have multi-armed robots, instead of saying there are two separate actions, we can introduce another parameter in the predicates, corresponding predicates, which is as you can see holding an arm empty, and introduce an arm number or something like that. So, we have arm 1, arm 2, arm 3, we can have any number of arms and we can simply extend the whole thing to that. So, this will of course carry forward to the predicates that are used, because now we have revised predicates as seen here, but it will also carry forward to the actions, and we just need to define the arm number or arm name, as the case may be, as a parameter for pick up, unstack, put down and stack essentially. So, we are simply saying that this arm is picking up or this arm is stacking something onto that, and so on and so forth. And that is a scene that we have used when we produce this partial plan that as a solution plan. We are deleting this, okay, that is not the scene we have used, but this other feature that I wanted to talk about is that you are adding this, you are deleting clear whenever you are unstacking or picking up, and that is a feature that we had used in the partial plan that we produced. In this example partial plan, we had still assumed that there are two actions, one is unstack 1 and the other is unstack 2, but we can easily modify it to adding 1 and 2 as a parameter instead. But the point that we were talking about also was that if you are going to delete the fact that the object you have picked up is clear, then you can actually no longer stack anything onto that, and which is why this action of stack 1D, action of stacking D onto C had to wait before C became clear, and C became clear after you had stacked C onto A on the right hand side, and that is why we had this causal link. So, how can we execute these plans? So, in this description, and by domain description 1 I mean this description where you are deleting clear A or clear X, as the case may be, from the description of the effects. So, in that description, initially of course we have two actions. So, we are just trying to see how will that plan be executed. The plan that we have just seen here, I have deleted the preconditions and effects and the causal links and everything, and I have only kept the 4 actions that are part of the plan, and I have only kept the ordering links essentially. Now, given that plan, how can it be executed? And we are interested in parallel execution to begin with. So, the first two actions, which were unstack actions, arm 1 is going to unstack D from A and arm 2 is going to unstack C from B, they can clearly be done in parallel irrespective of whether that deleting of clear is happening or not. So, there is no controversy here, but if you are using an action format in which we are deleting this thing that we are picking up, then at the next stage you can see that because you have unstacked C from A, it is the case that clear C will not be true, because it is deleted as depicted in this action. So, you cannot put anything onto C. You can do stack C onto A clearly, because that only requires this condition that A be clear, but you cannot do stack D onto C at this point, because of the fact that clear C is not true, and that is not true because of the fact that we have deleted it, we have added it to the delete list of that action. So, the only action you can do is stack C onto A, and that is consistent with the ordering links that we have. And in the next step, so now we have finished 2 time steps. In the first time step we unstacked both the blocks, in the second time step we stacked C onto A, and in the third time step we can now add stack D onto C essentially. So, let us look at the other possibility. The other possibility is when clear A is not deleted essentially. So, the action schemas look like this. that we are not deleting the object that we are picking up, we are not deleting clear B of that object that we are picking up. So, clear B could have been there in these two actions, but in this variation which we call as a domain 2 description, we do not delete clear C. What is the impact of that? The impact of this is that in this case, if arm N is holding B, either because of the pickup action or because of the unstack action, and clear B is true. Why is it true? Because we have not deleted it, it is not part of the delete list of the action. If there is another arm M which is holding B, which is holding A, it can stack A onto B. So, what is this situation? Arm 1 or arm N is holding B and arm M can stack A onto B. So, we can stack one block on top of another block. Not only can we stack one block, we can imagine in this situation that on arm 1, which is arm N in this case, you had B first, then you stacked A onto B, then you can stack C onto A, then you can stack D onto C and so on. You can hold the entire stack of blocks in one arm essentially. Of course, difficult to imagine, but you can see that that is possible. Also, if you are putting down B, you are holding B in arm N and you want to execute put down B action, and you also want to achieve A onto B, then these can be done concurrently. Now, it is again it kind of you have to extend your imagination a little bit to imagine that both the arms are putting down both the blocks that they are holding in such a way that one block ends up being on top of another block. So, that is why we called our multi-arm robot as versatile robots. With this kind of a condition, they can do all these kinds of things. In fact, not just two blocks, you can, if you had many arms holding, let us say n arms holding n blocks, then they could create a stack of n blocks in one time step essentially. Now, clearly that is mind boggling. As a small exercise, I would ask you to redefine the domain so that a robot can only hold a stack of two blocks. So, it can hold B for example, and you can stack A onto B, but you cannot stack a third one onto that. So, it is a small exercise that you should take up to see how that can be implemented. But at the moment we have a very versatile robot, and with this domain description, how does the plan look like? Okay. So, as before, both the initial actions which are to unstack the two blocks D from A and C from B, they can be done in parallel. So, there is no change here because there was no interaction between those two actions. But now we are assuming that when you unstack X from Y, it does not delete clear X, which means in these two cases at the end of these two actions D is going to remain clear because that was a precondition for unstacking D from A, and C is also going to remain clear because that was a precondition for unstacking C from B. And we have said that this unstack action does not delete that particular clear goal from this thing. So, now since C remains clear or clear C remains true, both the actions that we were talking about, they can be done in parallel. So, we can stack D onto C and we can stack C onto A. So, just imagine that these two actions, stacking D onto C and stacking C onto A, they are happening at the same time. So, both the robots, so sorry this it is not from here, but it is from the robot which is handling it. So, we have two robot arms, one is holding D. Let me draw this a bit neatly. So, this arm is holding D and it is going to stack it onto C, and this other arm is going to be holding C and it is going to stack it onto A. So, you can imagine that both these actions, these two arms have unstacked C and D respectively, and they are going to stack it simultaneously. So, D will be stacked onto C and A will be stacked, C will be stacked onto A, and this is what it means by saying that both these actions are happening at the same time essentially. Now, it also this is possible because in this new domain this stack 1 DC did not have to wait for C to become clear, and therefore, this causal link that was there in domain 1 no longer exists essentially. Okay, so, this is what we have seen so far, that the main key takeaway is that in plan space planning you can have plans which are partial orders, that is why it is also called partial order planning. Also, that ordering of the plans is left to as late as possible. So, it is also called least commitment planning. We will come back to this description in the next session and wind up the section on plan space planning. So, see you next time when we will look at plan space planning, and we will also look at where are the origins of plan space planning. They in fact go quite far back into the history of AI. Okay, so, see you the next time.